Okay, so here we have another optimization problem. This one deals with a cylindrical can. It's to be made to hold 1 liter of oil. Find the dimensions that will minimize the surface area of the can. Before I start this problem, I want to go to this and say that when we do our calculations, we want it to be some sort of distance measurement or mathematical measurement here, and liter is not going to be what we want. So if you remember that you can change out a liter with 1,000 cubic centimeters, that's what we're going to do here first. So 1,000 cubic centimeters equals 1 liter. Just kind of know that fact, and anytime you see a liter, change it to cubic centimeters. So we'll start there. Then I'm going to draw a picture. So I've got some kind of can, an oil can, where I need it to hold 1 liter or 1,000 cubic centimeters of oil. Okay, so if it needs to hold that much oil, that means that the volume needs to be 1,000 cubic centimeters. Okay, so find the dimensions that will minimize the surface area of the can. Minimize the surface area of the can. So I need to come up with what is a formula for the area of this can. Well, thinking about a cylinder, right? I'm going to have a radius down here for the base, and I'm going to have a height of the can. I don't know what those things are, but I know that those will be needed to find an area. And this oil can needs to have a lid. Okay, so we do need 2 of those bases. So essentially, we're going to have 2 of the bases, so 2 pi r squareds, right? So 1 pi r squared would give me the base. The other pi r squared would give me the top of the can. And so I have 2 of those. And then I also need the area all the way around the side. And the area around the side would be, essentially, you could look at this one of 2 ways. I've got the circumference of the base h number of times, right? So plus 2 pi r, that's the circumference of the base, times h. So this is what I want to minimize. I want to find the dimensions that will minimize this formula. And my constraint is that my volume needs to be 1,000 cubic centimeters. Okay. So if I think about the volume of this can, the volume of this can would simply be the base, the area of the base, pi r squared, times h. Right? If I take pi r squared and I multiply by h, then that means I'm going to take a filled-in area here, and I'm going to just keep stacking that filled-in circle on top of each other h times, right? And that would give me a filled-in cylinder there. So volume, pi r squared h, and then the area, I've got 2 of the bases plus the circumference times the height. Okay, so why did I do this? Well, this is going to be my constraint, that I've got the volume has to be 1,000. So 1,000 has to equal pi r squared h. If I only want one variable over here, I think what we're going to want to do here is to replace h. All right, because I've got an r here and an r here. I don't want to do that. I want to replace h, which means I need to solve this constraint equation for h so that I can replace and only have one variable. So I'm just going to divide by pi r squared. And so h would equal 1,000 divided by pi r squared. And now I can take this and plug it in for h over here. And that's going to give me an area formula of 2 pi r squared plus 2 pi r times 1,000 divided by pi r squared. Now before you start taking the derivative, obviously you want to simplify this as much as you can before you do that. It makes taking the derivative a lot easier. There's not really anything I can do with this 2 pi r squared, so I'm going to leave it. But if you look over here, what you can do is, if you think of this as being over 1, essentially I could cancel these pi's. I've got one on top and one on bottom. I could cancel this r on top with one of those r's on bottom. So I'm going to multiply 2 times 1,000, and then on bottom I'm going to multiply 1 by r. I still have one of these r's down here. So that second term is going to be 2,000 divided by r. And this simplifying process, might take a little while to get used to, but you're just essentially multiplying and simplifying there. That's about as simplified as I can make this. So what I'm going to do at this point in time is go ahead and take the derivative. You might want to, anytime you have a variable on bottom, you might want to, before we take the derivative, rewrite this as 2 pi r squared plus 2,000 r to the negative first. So anytime you have a variable on the bottom, bring it to the top and make it a negative exponent. It makes taking the derivative a little bit easier. So a prime is going to be 4 pi r. That's the derivative of this. Here I'm going to bring this negative 1 down, which is going to make this minus 2,000 r to the negative second. And now I think let's rewrite this again, because I need to find my critical numbers, and at this point in time that means we've got to solve for r, and that may look a little difficult right now. Or find what makes r makes this 0 is what I'm essentially trying to find. I'm going to take this r to the negative second back down to the bottom and make it a positive 2. So I'm going to have 4 pi r minus 2,000 over r squared. Then what you would want to do, so I'm trying to find the critical numbers. I set this equal to 0. So I want to know, when does this thing equal 0? And that's probably unlike any equation you've ever tried to solve before. What I would do is I would factor out a 1 over whatever you have on bottom here, so 1 over r squared. And what happens here then is this becomes, I still have that 4 pi, and I'm dividing, so I had r on top, and I'm taking out an r squared on bottom, which means if this were an r cubed divided by, or multiplied by this 1 over r squared, or divided by r squared, would give me back to this r. So however many more you have on top here than this, that's going to be the exponent. I need to add the exponent here to this 2, and that would give me 4 pi r cubed. That part might not make a whole lot of sense, but that's something that you're going to need to do there, and you'll catch on to that eventually, I think. Now this term just becomes minus 2,000, because this 1 over r squared, I took out that r squared out here to the front, and this has already become a lot nicer, because I don't have variables on top and on bottom. I just have one variable there. So now what I would do is I'm going to go ahead and factor out a 4 as well, since I can do that. So this is going to become 4 over r squared, and here I would just have pi r cubed minus 500, and I'm going to set that equal to 0. So when does this thing equal 0? Well, this part will never be 0. Right, so if I tried setting that 4 over r squared equal to 0, that's just not going to work, because a fraction is equal to 0 when the top is 0, and here the top is a constant, so it's never going to be 0. So I set this other part equal to 0. This pi r cubed minus 500, set that equal to 0. I add 500, I divide by pi, I would have r cubed equals 500 divided by pi, and now I can just take the cube root, and my r would be the cube root of 500 divided by pi. And now I want to do the test with this. So is this number the cube root of 500 divided by pi? What I'm trying to do is minimize. I need to make sure that this is a minimum. So I want to see that I go from decreasing to increasing, so that I hit a minimum at cube root of 500 divided by pi. You could, if you had a calculator on this problem, so that's not going to be guaranteed, but if you had a calculator on this problem, I would probably go ahead and get some kind of decimal for this, so I know numbers to pick on both sides. I know this is definitely bigger than 1, so I'm going to pick 1 over here on this side. Again, I don't want to go into the negatives because this is a radius of this cylinder, and I can't have a negative radius, and a radius of 0 wouldn't necessarily make sense either. So I'm going to pick 1, and I'm looking at this most factored form, which was right here. And I'm saying, if I plug in 1, what kind of number do I get? Well, 4 over 1 squared is going to be positive. And if I plugged in 1 here, pi times 1 cubed minus 500 would be negative. And so it's going to be negative, which means I'm going to be decreasing there. If I pick something to the right of the cube root of 500 divided by pi, and again, I do kind of have some constraints here with the r's that I can pick. But, you know, pick something that's going to be bigger than this number, so that might be a case where I would want to have a calculator to figure out about where this number is at. You could somewhat estimate about where this number would be, but I would say, you know, if you pick 100, that's definitely going to be bigger than this number, because 500 divided by pi, so essentially dividing by 3 and then taking the cube root of that, I'm going to get definitely something smaller than 100 there. So if I plug that in, I would get a positive from that 4 over r squared, and I would get something here that's bigger than, you know, when I cube it and then multiply by pi, it's going to be bigger than 500, so when I subtract 500, it's still going to be positive, which means this is going to be increasing on this side, which does mean that this is a minimum, which is what I wanted. So the minimum happens, the minimum surface area of this can happens whenever r is equal to the cube root of 500 divided by pi. Again, you could get a decimal for that if you would like. I need to know all the dimensions, so I need to know the height as well, and I'm going to go back to this and say then the height would have to be 1,000 divided by pi times what I got for r, which is the cube root of 500 divided by pi squared. And I'm just going to leave my dimensions like that. If you want decimals, go ahead. Those numbers are going to make more sense to you. But these are the dimensions that I need for r and h to minimize the surface area of this can that needs to hold 1,000 cubic centimeters of oil. Okay, so that problem is a little bit more involved than the rectangular one, but you know they really don't get too much more difficult than this problem. You know, it's kind of an ugly one, and so you know, we just need to be able to use geometric formulas, and that could be the problem. You know, if we can't get this formula right off the start, kind of like related rates, we're going to have trouble doing the rest of this problem. Next video I'll do one more example of an optimization problem, and then we will practice some in class.